Okay, guys, I think we're going to be starting now. Just a little comment before we start everything today. Please shut down your microphone and your camera if you're not the speaker, of course. On behalf of the BTL, I would like to welcome all of you with us today. We have decided to dedicate December to Power to X technology, and we're pretty happy today to have a very important group in Iceland, represented by Benedikt Stefánsson. Benedikt Stefansson is Director of Business Development for Carbon Recycling International in Iceland. Before joining in CRI in 2010, Benedikt served as advisor to the Icelandic Minister of Economic Affairs, and held senior position in banking and biotech. He did his PhD study in economics at the University of California, Los Angeles, and Keio University in Tokyo, and received his bachelor's degree in economics from the University of Iceland. So an overview of the company, briefly, Carbon Recycling International is an Icelandic technology company developing and implementing process technology to produce low carbon intensity methanol from carbon dioxide and hydrogen. The company was founded in 2006 and is privately funded by investors from Iceland, Canada, China, and the US. In 2012, CRI commissioned the world's first industrial-scale liquid electrofuel e-fuel plant. The plant, based on CRI's proprietary emission-to-liquid technology, utilizes 100% renewable electricity from the Icelandic grid. CRI recently implemented the ETL system in Germany and Sweden, and the company is now preparing to launch the first commercial scale ETL plant in China. So the title of the presentation is CRI CO2 to methanol technology and a perspective on the regulatory and commercial landscape for PTX with carbon capture and utilization. And once again, we're really happy to have Benedikt with us today. It's an honor to have you with us. Thank you again. And without further ado, the floor is yours.
Thank you very much. So let me just go through the rigmarole of sharing my slides and such. Okay. All right. I hope everybody is seeing the slides on their screen, and then I can start. So this is a bit of a shorter version of the title. So without further ado, today what I would like to share with you are, first of all, of course, some milestones in the development of this technology, and also how we are sort of integrating ourselves with this new technology into the value chain. Some basic techno-economics and LCA, which is very important in this context. And then I want to talk about the competitive and regulatory landscape for low carbon intensity fuels and chemicals, and of course, specifically the product that we are producing, which is renewable methanol. And then some sort of my perspective on future opportunities and challenges. So the first thing I wanted to just mention is, of course, to set the stage a little bit, is the overarching problem that we were trying to solve, which is, of course, that very, very dependent on fossil fuels, as we all know, which then, because of when they're combusted, they cause CO2 emissions and greenhouse gas emissions, cause climate change, ocean acidification, and then not the least of all, urban pollution. So essentially our task as a generation is to get rid of this dependency on fossil fuels. But that is going to be hard. And one of the things that makes it hard, of course, is that our heavy and long haul transport depends heavily on these energy-dense energy carriers that the fossil fuels are. And it is going to be very, very difficult for us to electrify this part of transport, for example, which will then also depend on the aspect of liquid fuel, which is much easier to store and transport. Electrification is the key to solving this problem, but we actually face a very peculiar problem, is that we have an abundance of renewable energy on the Earth, but the location of this energy and its availability in terms of timing does not match the location and the hours of demand. So this is, of course, why our company exists. We wanted to bring in a solution which allows you to transform stranded electricity, whether it's in time or space, into clean burning liquid fuel for the reasons I mentioned before, and we have focused on, and this process can be entirely carbon neutral. So as mentioned earlier, we were launched here in Iceland in 2006 by a group of entrepreneurs, which then developed the CO2 methanol process in a laboratory, and then eventually built and operated the first industrial scale plant here in Iceland, which was commissioned in 2012. As you can see from the flags on this slide, we have done projects elsewhere as well, which I will tell you about in a second. So the company today basically focuses on the full value chain of renewable methanol. So we have experience in selling this fuel, and it's very important to integrate this new form of renewable fuels into the existing frameworks, and then of course elaborate and change the frameworks. So we've been very active also on advocacy, certification, verification of LCA and so on. And we were the first ones to certify an electrofuel for the European market, which also started at the same time as when we commissioned our plant. And again, the flags tell you that we have actually been selling and using the product in many more countries than just here in Iceland. Today, we are essentially a technology provider at heart. So we are in the business of implementing commercial scale CO2 to methanol plants in both Europe and China, and hopefully we will also be active in North America, in Canada included, in a short while. This is a schematic of the platform that we are talking about. So we call this the emissions to liquids technology platform. So it consists essentially of three modules, basic modules. There's the CO2 capture and purification module. There's the module that supplies hydrogen, which can either be from electrolysis, water electrolysis, can be from byproduct hydrogen from industry. The third module is our core technology, the actual emissions to liquids technology platform, which consists essentially of three sub-modules. There's the compression aspect, where you compress the two gases, CO2 and hydrogen, which is the only elements that we need, and then the reactor, and then subsequently the distillation module, where we remove the water that is also formed in the reaction, as you can see from the chemistry. Now, to put a little bit more detail on this slide, what you see here is essentially the energy mass balance for this flow of materials and energy. As you can see here, basically we need 200 kilograms of hydrogen per ton of methanol, which we can either obtain by electrolyzing water, in which case we of course take in water and electricity and split that into oxygen and hydrogen. But we could also as well be relying on other industry to supply the hydrogen. So for example, steel industry, which is represented by these icons, is an excellent source of byproduct hydrogen. And I will tell you a little bit more about what we've been doing on that front as well. Now, the oxygen, of course, does not go into the process. It can be then sold or put into another company. In addition to the 200 kilograms of hydrogen, we use 1.45 tons of CO2 per ton of methanol, which then, as I mentioned earlier, has to be compressed. The two gases then at high pressure are reacted, and they form both methanol and water. And that is then the water is removed by using heat. So we import a little bit more of electricity for the compression stage and some other valves and pumps in the plant. And we also are net importers of heat, at least at the moment, but we are able to scavenge waste heat from the reaction to meet most of the heat demand. In addition to the methanol that we produce, we also produce, of course, water from the distillation system and what we call fusel oil, which is a mixture of basically methanol and a few higher hydrocarbons, but that is a very minute amount. That in terms of the effluents. So the main ingredient or the main additional production is in form of the water. You can also see there the energy balance essentially. If you just look at if you add up the amount of electricity that we use and then compare that to the heating value of the methanol, you will see that we are approximately at a level of approximately 50% end-to-end efficiency. And if you want to break that down further, the electrolysis part is roughly 70% efficient. can be made more efficient, of course, over time. And then the basic reaction is roughly 70% efficient in terms of the energy in the gas to the energy in the methanol. But the overall efficiency of the system is much higher than that. Of course, it's about 85% or so, and about 95% if you're just looking at carbon efficiency, how much of the carbon or the energy that we are inputting, or the gases we can actually return. Now, in terms of LCA, what we're trying to do, of course, as I mentioned earlier, is to reduce our dependency on fossil fuels and reduce the life cycle emissions of these energy carriers. So the easiest comparison to make is with fossil fuels. That is already done on a regulatory basis, for example, by the European Union, where we have a reference standard for the emissions that occur when you produce or make distillates, gasoline and diesel. And then, of course, the tailpipe emissions or the combustion emissions that then are result from the use of that fuel. And that is what we're trying to offset. So we take in CO2 that gets embedded in the product, but pretty much the equal amount of CO2 that we capture and utilize is going to be released. But that CO2 is considered to be neutral because it would have otherwise been emitted or can come from a neutral carbon source. And if we use industrial emissions, that is allowed, even though they are, of course, originating from fossil fuels, they would have gone into the atmosphere otherwise. So as long as we can show that these emissions would have occurred, then they are considered to be neutral. And so what is remaining essentially is the carbon footprint of the energy that we use. And in most cases, we are now considering with electrolysis plants that are in systems which are already 100% renewable. So Iceland is one of those cases. Norway is another. And increasingly in Europe, we're seeing several countries which are approaching the 80 to 90% level in terms of grid electricity being renewable. But with 100% renewable electricity, we are offsetting roughly 3.6 tons of CO2 emissions per ton of oil equivalent. Now, if we look at this from a chemical perspective, because methanol is also used widely in organic chemistry and can also be a substitute for natural gas, for example, in making polypropylene and polyethylene, which then can make basically any synthetic material. You'll have to look at it slightly differently because now the CO2 or the carbon is sequestered in the product, and then you have to basically compare this to the amount of release of CO2 and use of fossil fuels, and you get a net amount, which is about 4.2 tons of CO2 per ton of oil equivalent. We have certified this in terms of the fuel space with ISCC, which is the largest agency in the world in terms of the certification of biofuels, and has adapted their system to use for this electrofuel process. And we have also been audited by a company called SGS in Europe, but there are other auditors that would be able to do this work as well. And this is very, very important for the market to have these systems worked out so that everybody who's acting within this space, taking in these new types of fuels, has certification and verification of the actual CO2 abatement. Now, our company started, as I mentioned earlier, in 2006, and by 2012, we had commissioned the first industrial scale unit here in Iceland. It is actually a sizable plant in itself. It takes in grid electricity from the Icelandic grid and CO2 from an adjacent geothermal power station. And we can produce 10 tons of methanol per day. That is 4,000 tons of methanol per year. Then our next two projects were outside of Iceland, one in Germany last year and one in Sweden, which has just concluded. The one in Germany was focused on demonstrating that this system, the synthesis system, can be load following and actually adjust to intermittent levels of energy. In this case, an electrolyzer, which was attached, of course, was being run on a simulated profile of wind energy, so it would go up and down frequently, and the synthesis system had to adapt in real time. This system that we built was actually smaller than the one we have in Iceland. It's only 1 ton per day, and it's actually transportable. The CO2 came from a lignite coal power plant. The next step, this project that we have just concluded up in the very far north of Sweden, was based on a very different approach. In this case, there was an existing research project to show that you could take blast furnace gas and through what is called a sorption enhanced water gas shift, shift it into carbon dioxide, shift the carbon monoxide, from the blast furnace gas into carbon dioxide and hydrogen, which then are the raw materials that we need. The carbon hydrogen balance, however, is not correct. So you have to augment that that gas with additional hydrogen, which we obtain from electrolysis using Swedish national grid electricity. It's the same scale of system, 1 ton per day, and both of these projects that I've mentioned here are funded by the European Union in part under what is called the Horizon 2020 program. But then is the flagship project at the moment, which is the next step in the evolution of this technology, which is to go to full commercial scale. So going from the largest plant we've built to date, which has a capacity of 10 tons per day, to 330 tons per day, which will be a true commercial scale project, 110,000 tons per year. In this case, we are also using gas from the steel industry, and no electrolysis is involved. The gas in this case is from the front end of the steel process, the coking oven, gas which is very rich in hydrogen, so you can separate that out with a membrane. And then we get the CO2 from basically a part of the petrochemical process, which is a lime kiln. And the customer, which is paying for the funding the project in total, and buying basically this engineering package and technology license from us, will be using the methanol both internally and also in transport in China. So this project will be fully commissioned in the first months of 2022. And in terms of using water electrolysis and therefore renewable electricity, we are now in the process of developing a project in Europe, in Norway, with Statkraft, which is the national power utility of Norway and also the largest renewable energy company in Europe. This will be of a similar size as the project in China, so 100,000 tons per year, or about 300 tons per day. And will utilize, as I said, electricity for electrolysis. So this will also be the largest electrolyzer farm in Europe and perhaps in the world when built, using 120 megawatts base load for electrolysis and another approximately 10 megawatts base load for other systems in the plant. The source of this CO2 is a ferrosilicon smelter, and one of the collaborators in the project is also the ferrosilicon company. So this is a diagram that explains a little bit more how we then interact with the upstream CO2 emitter and also within the energy system. So the ferrosilicon plant already scavenges waste heat to produce steam, which is then used in power production. Some of that heat will now be also released to our plant, as well as, of course, the CO2, or rather the flue gas, which we then will use an amine system to, where we will use an amine system to capture the CO2 and concentrate. Electricity will be coming from the Norwegian grid. The ferrosilicon plant will continue to sell some of the power to electricity generation. As a part of the project, the ferrosilicon smelter is actually also developing algae cultivation using CO2. So we will be using part of the CO2, and the other process will have access to part of the CO2. As I said, this plant will have a capacity of 300 tons per day of methanol. And that will be able to go into the fuel sector here in Europe, but also chemicals as well. So in a few years, we have therefore been able to go all the way from liters to tons to a sizable demonstrator here in Iceland, and now these 300 to 330 ton plants, which will be, the first one will be commissioned in 22. But let me take a quick step back and tell you a little bit about methanol, which you have heard me now mention several times. But Just to clear up any confusion between methanol and methane, it's of course a liquid. That's one of the reasons why we want to produce it and use it. It is normally produced using a steam methane reforming process in which you take natural gas, CH4, and crack it to make syngas in order to then recombine and make the methanol. That process, of course, therefore relies heavily on access to fairly cheap natural gas. We don't have much in common with this process, except maybe you could say that in the overall scheme of things, you also end up with water and methanol, which you have to distill. And we have developed a lot of our technology independently of this steam methane reforming process. And one of the things that people often get confused about is that they expect us to be producing the methanol from syngas, which of course is what you obtain from the steam methane reforming. And but we don't go through that route. We go directly from CO2, a very inert molecule, of course, and hydrogen in one step to methanol. We, of course, because of the additional oxygen in the CO2, we obtain a little bit more water than you do in the steam methane reforming process. But fortunately enough, methanol is and water are very easy to separate because of very separate boiling points. Now, the normal methanol has traditionally always gone into chemical applications. That is changing, especially because now over half of the market for methanol is in China, and China has invested heavily in methanol to olefins processes and also started to use a large portion of its methanol for energy applications. So that can be both in cars, but also in other energy applications such as industrial boilers, cook stoves. A lot of restaurants in China now use methanol because it burns so cleanly. Now, if I switch back to the rest of the world or the overall scheme of things, the largest portion of methanol goes into making resins, paints, and such through formaldehyde, acetic acid, and also other processes. Now, methanol also is very interesting as a fuel because of its very high octane, which is shown in the graph that you see on the slide. You see that this is a single carbon atom with no carbon-carbon bonds, cannot create any soot when it is combusted. That is one of the aspects that are attractive. And it also holds basically more hydrogen per carbon atom than any other fuel. That then also relates to the fact that the specific CO2 emissions from combusting methanol relative to gasoline are only about 90%, which is actually also a reflection of efficiency in combustion. So it has been shown that you can basically lower energy consumption in a normal gasoline engine by switching from gasoline to methanol. So our process, as I said before, is distinct, different from the normal reforming process. On the
Benedikt, I'm sorry. I think you're muted. I think your mic is muted.
Okay, I don't know when that happened. Somebody seems to have muted me. I don't know how it happened. Sorry, was that just this one slide or more?
Yeah, it's just this one slide.
It just happened.
Okay, so sorry. Okay, so let me just continue. So, we have maybe one of the distinctions that we have is that we have now a industrially validated system performance over tens of thousands of hours under normal industrial conditions. And we have also demonstrated that this system is very, very safe for the operators. We're working with lower pressure and lower heat than many other systems that you might consider. In terms of the fuel utilization, I've already mentioned several of the points on the right-hand side. The aspect that you have a single carbon atom with methanol and some of its derivatives, such as DME, which produce no soot, no sulfur, is ultra low in NOx emissions, with basically very low cost in making that NOx go away, and very low in toxicity actually compared to many other fuels. It is higher density than gases and batteries in terms of energy density. Of course, lower energy density than fossil fuels that we know, but basically the lower energy density is something we have to live with if we are using oxygenates such as ethanol, or if we're using biodiesel instead of diesel. And but the important part is that the confrontation with hydrogen and with battery operation. And on that aspect, of course, liquid fuels are much better. It is, as I mentioned, a pathway to increasing the efficiency of combustion engines, and it's also a pathway to switching from combustion engines to fuel cells, because there are now many producers of direct methanol fuel cells. So the
Sorry, Benedikt, your mic is off again.
Yeah, sorry, this is some bug in the system. Okay, I hope I'm back online. Can you hear me now?
Yes, it's fine.
Yes.
Okay, sorry. Okay, so you know, I've mentioned this several times that the issue, of course, at hand is to defossilize, and people are often very caught up in that they want to do this, especially in transport with electricity. And why is transport, of course, also another focal point? Is because if you these are all numbers from the European Union, so only for Europe, but this applies to the rest of the world as well. Is that transport has been behind in the evolution, while most in Western countries, at least, industrial sectors have been quite kind of efficient, so to speak, in reducing CO2 emissions. Transport has not done that. So there's a wide gap between the evolution of these two sectors. If you look at transport, when you break it down, actually, of course, there's the lure of the battery electric vehicle for urban transport and some forms of mass transport as well in urban areas. But you know, the amount of fuel that is used by the small and medium car population is actually quite low in comparison to the rest of the utilization of fossil fuels. Now, methanol, as I mentioned before, has a wide variety of uses. You know, even when everything is said and done about fuels, we will still be needing all of these hydrocarbons for industrial applications. As I mentioned earlier, there are traditional uses of methanol, such as through formaldehyde and acetic acid into textiles, adhesives, paints and coatings, etc. But there's also the opportunity to actually do all of the chemistry that you do today through ethylene and propylene by starting with the methanol precursor, or the methanol process rather, and with the methanol to olefins process in between. One example I wanted to show you just quickly, or a couple of samples in the chemical sector before I go on with more about fuels, is, for example, this utilization of resins in the wood industry, which might be of interest for Canada. Formaldehyde is a precursor for formaldehyde urea resin, which is then used, for example, in making laminated wood and fiberboard. And what I'm showing here is essentially that through this renewable methanol pathway, you can increase the amount of carbon that is embedded in the glue by about a half. So you end up with, per ton of glue, roughly about 0.6 or 600 kilograms of additional CO2, which would be coming in through this process of CO2 to methanol. Another thing that we have sort of stumbled upon, so to speak, is that in water purification, which is done for raw sewage in urban areas, there's a very important step at the end, which is called the denitrification step. In essence, you have a bunch of bacteria living in this